And so what this talk is about is the application of techniques for studying, I guess, modelized spaces of surfaces to general linear groups of the easiest rings you can think of, which are infinite fields. Our results are, this is joint work with Soren, Galatius, and Oscar Randal-Williams. Our result is a bit more general. So many of the results I'm going to tell you about, we proved for semi-local rings with infinite residue fields, but for the sake of exposition, this entire talk, I'll just restrict to fields. So it's not maybe K-theory the most exciting rings of schemes you can think of, but it's rather maybe a relationship of algebraic K-theory to the unstable homology of certain groups. And there's lots of interesting links that I think haven't really been fully explored. So I'm gonna, during this talk, take some detours and tell you about some conjectures that, as far as I know, are still open, that are related to how the unstable homology of general linear groups of fields is related to the algebraic K-theory of those fields. Okay, so let me start by stating two conventions. The first one is one that I already said, which is that basically all rings that appear are going to be fields and infinite fields. Or at least we're going to have the property that every finitely generated projective module is free. And the second convention is that any functor or construction that I described will be derived. So that means that either you work with infinity categories, or I'm asserting that there exist certain suitable model structures on the categories involved with respect to which you can derive these functors.
And I guess, are you omitting finite fields because they're already understood, or because this method doesn't help?
I'm omitting finite fields. The method does help in that case and proves new results, which is in a different paper of ours. There's going to be one property, which is called which we call the Nesterenko-Suslin property, which doesn't hold for finite fields. And it's that property that allows you to prove some very strong results, which are mainly the source of our new results. So in some sense, the results of this talk don't apply to finite fields. If you want to get the technology to apply to finite fields, it does, and the answers will be slightly different. Okay, so I'm going to start very basic, and you probably already know a lot of this stuff, but just to set the stage. So we all know what a definition of K0 is, right? You take the monoid of isomorphism classes of finely generated projective A modules. Under direct sum. And you take its group completion. In other words, what you do is you take the free abelian group on these isomorphism classes, let's call them P, and you impose the relation that, the sum of two isomorphism classes is equal to the isomorphism class of the direct sum. So under the assumption that I made in the beginning, it's actually very easy to compute what the answer is. The assumption was that all finely generated projective A modules are free, so they're uniquely determined of the isomorphism by their rank. So the rank induces a homomorphism from K0 to Z, which under the assumption that we used is an isomorphism. Okay, and the higher algebraic K-theory groups, well, you get them by doing a homotopical version of this group completion construction. So the first thing you do is replace the isomorphism classes of these finely generated projective A modules. You replace them with the moduli space of such modules. So what that means is you take for each isomorphism class a single space given by the classifying space of the automorphisms of that module. So in this case, the isomorphism classes are a to the n for n greater than or equal to 0. The automorphisms of those objects are gln of a. Maybe it would have been better to write this as the geometric realization of some category, and I actually will do so later. Okay. So how is this a topological monoid, right? The right-hand side was a monoid. Sorry, the left-hand side was a monoid. The right-hand side would be a topological monoid. Well, that's by block sum. So there are homomorphisms from gln a times glm a to gln plus ma, which take some n by n matrix and an m by m matrix to the block sum. Okay, and so this induces a map on classifying spaces, and then induces a map on those, and the disjoint union of all these classifying spaces. Okay, and so what we do is replace the group completion of monoids with the group completion of topological monoids. So there's many ways you can do that. As an entire study of machinery that allows you to do this, but let's just use Siegel's construction. So we take loops of B, this monoid. So B here is the usual bar construction. Loops is base loops. Okay, and then the algebraic K-theory groups of A are just defined to be the homotopic groups, this space. Now, this space is a loop space. Right, I mean, it's literally by construction loop space. So it doesn't really matter which path, which base point I take. That's why I didn't write that down. But maybe more importantly, this means it's a simple space. For each path component, the fundamental group acts trivially on the higher homotopy groups, which means that there's a strong relationship between its homology and its homotopy. So one thing you could try to do if you want to study algebraic K-theory is to study the homology of this group completion. And one way you could do that is through the Magdev-Siegel group completion theorem. So what the theorem does is give you a description of the homology of the group completion in terms of the homology of the finite general linear groups, the GLN of A's. So to describe it, I need to give one instance, I guess, of a block sum operation, which is called the stabilization map. So it turns out there's homomorphisms from gln of A to gln plus 1 of A, which just add to a matrix N a single one in the bottom right corner. So let's call this sigma. Okay, and this induces a map on classifying spaces. And hence induces a map on these disjoint unions. And what the group completion theorem says, I mean, there's some conditions need to be satisfied, which are satisfied in this case, is that the homology of the group completion is what you get when you take the co-limit over this map sigma. Okay, in particular, if you just want to know the homology of one path component, and that's the same as knowing the homology of any path component because it's a loop space, that's just the co-limit as n goes to infinity of the homology of BGLN of A, where we use stabilization maps to form this co-limit. Okay, so if you can understand the homology of the BGLNAs and the stabilization maps between these homology groups, you could in principle get information about algebraic K-theory. So I should point out that this is not the most efficient way to compute algebraic K-theory at all. I know it's useful in only a few cases. Those cases are mainly for low degree algebraic K-theory groups. So maybe up to degree, including degree 3. And in special circumstances like finite fields, or for if you want to compute a rational algebraic K-theory of rings of integers using the work of Borel. So maybe this is Quillen. One thing that makes your task a bit easier is that you don't need to know all of these homology groups and all of the maps between them to carry out a program like that. You only need to know a few of them, because for many rings, particularly the ones that we're going to consider, there's homological stability. So what that says is that the map from the homology of GLn-1 of A to the homology of GLn of A, this is an isomorphism for star, well, let's say much smaller than A. There's a range of degrees in which it's an isomorphism tending to infinity with n. The exact range depends on the stable rank of the ring. Okay, so if you're interested in trying to get information about K8 through the homology of general linear groups, which is in some sense how we are able to compute K8 of the integers, you only need to know the homology for a few of the general linear groups. So in general, when you prove results like this, both for phrasing them in the sharpest possible way and for proving them, it's better to use relative terms. So these stabilization maps, being isomorphisms or surjections, of course, can be rephrased in terms of the relative homology vanishing. Okay. So let me just give you an example of a homological stability result that you can easily read off. Just show you that this is a phenomenon that happens pretty often. And that's for H1. So H1 of BGLN A, that's of course just a binization. Okay. Now, the determinant is a map from GLN A to A star. In particular, it's a map into an abelian group, so it factors over the binization. And this is an isomorphism for n at least 3 if A is a field. Okay, why is this true? Well, that's because in that case, SLN, the kernel of that map is perfect. Which is something you can check by like writing it in terms of, writing SLN in terms of elementary matrices. So this is something you could have proven yourself. In particular, what this tells you is that H1 of BGLN of F relative to BGLN minus 1 of F is 0 for n at least 3. Okay. Now, if you're dealing with an infinite field, we have the strongest possible stability results. So that's a theorem of Nesterenko and Suslin. So they proved the following result. So the first thing that they proved is that these relative homology groups vanish when star is smaller than n. Okay, so this is a slope 1 stability result. The coefficient in front of n is 1. For most other rings, it will be 1/2. But they also proved that this is sharp. And they did this by computing the next relative homology group. So what they proved is that this is isomorphic to the end Milnor K-theory of the field. Okay, so what is Milnor K-theory? Well, it's the graded ring generated by symbols A, where A is a unit. These symbols live in degree 1, subject to the relation that the product is 0 if the sum is equal to 1. Okay, so if you know about how Milnor K-theory usually appears, this is quite surprising, because usually Milnor K-theory appears as follows. And you can actually do something from the fact that it appears in the unstable homology of general linear groups. So yeah, whenever a group is a homology group of a general linear group is not in the range where the stabilization map is an isomorphism, we call it an unstable homology group. Okay, but let me explain the other way that Milnor K-theory appears. So we used direct sum of finely generated projective A modules to make, well, to construct the algebraic K-theory groups. We didn't just use that, there's also a tensor product. And so tensor product, what it will do is make the algebraic K-theory groups into a graded ring. I mean, it's in fact graded commutative, but I'm not going to use that. We also just computed for an infinite field what K1 is, right? We computed what stable H1 is going to be. It's going to be F star. And then using the fact that the group completion is loop space, that tells you that pi 1 is also F star. So K1 of F is F star. What you can look at is the subring generated by these elements. Or rather, you can look at the quadratic ring generated by it. So there's of course a map from the tensor algebra on F star into here. Some relations, quadratic relations, are satisfied in algebraic K-theory. In particular, the Steinberg relation, which is the one I've listed here, is satisfied. So this map factors over Milnor K-theory. Okay, so we get a map from Milnor K-theory to K-theory, which is constructed in a completely different way than Milnor K-theory appears in the previous theorem. And now you can do the following. So you can consider the following long sequence of homomorphisms. You can take Milnor K-theory, use this construction to map it to K-theory, use the Horerich map to map to the homology, oops. Okay, sorry, let me fix the degree. To be n. Now you can use these stability isomorphisms to identify this colimit with the homology GLN. Of F. So such a long chain of homomorphisms, I need more space. Now we can map to the relative homology. And then this theorem of Suslin and Nesterenko identifies this with the end Milnor K-theory again. So we have Milnor K-theory mapping into K-theory and through this long sequence of homomorphisms mapping out of K-theory, and this long diagonal map, this is multiplication by n-1 factorial. So one thing you can gain from studying the unstable homology of general linear groups in this particular case is that you can show that after inverting some primes, Milnor K-theory splits off K-theory. In particular, rationally it splits off. Okay, so what I'm going to do in this talk, I'm going to explain an alternative proof of this theorem of Nesterenko and Suslin. And I'm going to tell you something about what happens the next line up. And so, as you can see in my statement, what happens depends a lot on whether the Milnor K-theory is a causal ring. It's a quadratic ring, so you might ask whether it's causal. If it is, we get quite a strong result. It's a conjecture of, I guess it follows from conjectures of Parshin and Beilenson, that if F has finite characteristic, then it is causal. What it's supposed to be generated by is something like the block group and some things built out of units. Okay, So the strategy for proving this Nesterenko-Suslin theorem and giving this result for the next line is to take the disjoint union of the classifying spaces of general linear groups, consider them as an E-infinity algebra, try and build a presentation for them, and from that presentation, then deduce these results about the unstable homology groups. Okay, so before getting to that, let me just talk a bit about K algebras and their homology. Okay, so our starting point is the observation that the disjoint union of the general linear groups of a field is an E-infinity algebra. So this is like a commutative algebra in a homotopical sense. One thing to point out at this point is that I'm taking n to be at least 1. So I'm going to work with non-unital infinity algebras or EK algebras. Equivalently, you could work with augmented ones. So we'll sometimes do that. Okay, so let me just explain in an example why it's at least homotopy commutative. So to see it's homotopy commutative, what you have to check is that the map induced by taking this block sum on classifying spaces is homotopic to the map induced by this block sum on classifying spaces. And you may recall that if you conjugate on a classifying space of a group by a group element, that map is homotopic to the identity. And these two ways of doing block sum, they differ by conjugation with the element given by these identity matrices. So here's, well, maybe one thing that you can notice if you're thinking about how you might generalize some of this stuff. If you would study special linear groups, which is also a very reasonable thing to do, this will no longer work because this element here might have determinant -1. So Soren Galatius has a student, Glista Bernhard, who's working on dealing with this particular case. Okay, so to describe the infinity algebra on this object, it's helpful to work a bit more generally. One reason I'm working more generally is because eventually this will also allow me to describe EK homology in terms of buildings. Okay, so my starting point is going to be the following symmetric monoidal category. The objects are going to be finally generated projective modules. The morphisms are isomorphisms, and the tensor product is direct sum. Okay, so whenever I have a symmetric modal category like this, the category of functors from it into simplicial sets is going to be symmetric modal as well, using day convolution. Right? What you do is you define a tensor product by taking the left scan extension in the following diagram. Okay, so this is going to be the tensor product. Okay, So once you have a symmetric nodal structure, you can make sense of non-unital infinity algebras in this category. And what I'm going to use that as a very easy to describe canonical such non-unital infinity algebra. In fact, it's going to be commutative. So this is an object we call star underline greater than 0. Okay. What is this going to be given by? So it's a functor from this category to simplicial sets. It takes the empty set on the 0 modules, and it takes the value given by the point on the non-zero modules. Okay, and there's really only one way you could make this into a commutative or infinity algebra. Okay, so what I'll do is construct the object I'm interested in, this disjoint union as an infinity algebra from this. So what I do is use that if I take my ring to be a field, A is equal to F, then the dimension, but let me denote it R, gives a symmetric nodal functor from this category to the natural numbers with addition. Okay. So from this, I get an adjunction. I can restrict a functor from IPA into simplicial sets along R, that's R upper star. This has a left adjoint, R lower star, which goes from functors from simplicial sets. Sorry, from IPA to simplicial sets to functors from natural numbers to simplicial sets. And this takes infinity algebras to infinity algebras. So what I'm going to do is set R to be the derived functor of R lower star applied to this canonical infinity algebra. Okay, so what is it explicitly given by? Well, R lower star, what it does is take the homotopy quotient by the automorphisms of the objects. So the underlying object is given by sending a natural number n to, well, there's two things. Either the empty set homotopy quotient by GL0, which is still the empty set, if n is 0, or the point homotopy quotient by GLN of f, if n is 1. So indeed, if I forget about this additional grading by n, we'll call that rank. So forgetting the rank, we really do get the disjoint union of these classifying spaces. Okay. So since we're interested in homology with coefficients in some commutative ring.
Yep. Sorry, a question from Jan Rognes. So n is greater than equals to 1.
Yeah. Yes. That is correct. Right, so here I wrote n is 1, it should be n greater than equal to 1. Okay, so since we're interested in taking homology with coefficients that are either going to be z or q, and really you want them to be z, q is only there for simplicity in some of the exposition. We're going to take chains on this. Okay, which I'm going to think of as taking the free simplicial K module on the simplicial set. So this we have the property that the homotopy of RK N is just the homology with K coefficient of B GLN of F. Okay, so one thing I didn't explain yet in detail was what an infinity algebra is, though you probably are familiar with it. Well, they are algebras over an operad. You can take many models. We're going to take some infinite little cubes operad as an example of this. So it's the co-limit of the little k cubes operad. So what it means is it's an algebraic object whose operations are indexed by the space of embeddings of little k cubes into a larger k cubes. So if I take k is equal to 2, then for example, the three array operations are indexed by the space of disjoint little 2 cubes in a large 2 cube. Okay, and these all include into each other by taking the product with an interval. And we can take the co-limit over that. So these operads encode increasingly commutative algebraic structures. What do I mean by that? Well, if I had looked at the space of 2 array operations, right, that's just homotopy equivalent to a k minus 1 sphere. And so as k goes to infinity, you get something contractible, but before that, it's already highly connected. And so it's commutative to some degree. Okay, so we're also going to need EK algebras, which are algebras over these operads of little k cubes. And the particular cases we're interested in are going to be 1, 2, and infinity. And 2 will play a very special role, which I think was something we didn't expect at first. Okay, so the strategy is going to be to give a presentation of R of Z or R of K as an EK algebra. In the end, the theorem that I mentioned is going to be deduced from the case K is infinity, but we'll also have uses for the case K is 1 and K is 2. So what do I mean by a presentation? I mean writing it as a cellular or CWK algebra. So you all know how to attach a cell in topological spaces, right? You start with some space X. You have an attaching map. You include the boundary of the cell into the cell, and you take a push out. So basically the same construction works in EK algebras in simplicial K modules, well, functors from natural numbers in simplicial K modules, if you make the obvious generalizations. So the first thing you have to do is replace these disks and their boundaries by functors. So we're going to take, for example, the bottom one to be the D cell concentrated in rank n. So really these are functors. And now you can't just take a diagram like this and take the push out where A is some EK algebra. Because of course, the left-hand side is not an EK algebra. So this diagram doesn't even really make sense. What you can do is map into the underlying object of A, apply the forgetful functor, which has a left adjoint, which is the free EK algebra functor. So you do get maps, a diagram like this. And now you take the push out. Okay, so what this means intuitively is that you attach this cell to A, then some operations from the little K-disks, K-cubes opera apply to elements of A with this disk attached might not be defined. You just freely add those in. Okay, and so a cellular EK algebra is one obtained by iterating this construction. So let's say as a sequential co-limit of these types of cell attachments. So let's call them EK cell attachments. If I were talking about model structures on these categories, these would be the prototypical cofibrant objects. Okay, so notice that these cells are not attached in the order of dimension. So that's something you might want. So if you require that, you're led to the notion of a CW EK algebra. So it's a bit more than just requiring that the cells are attached in order of dimension. It's really data. So this is a EK algebra in filtered objects where the d-dimensional EK cells are attached in the D filtration step. Okay, the reason you want this to be your definition is that what makes CW complexes powerful in algebraic topology is that you have a skeletal filtration that you can use for inductive arguments. And we want to do something similar for EK algebras. Okay. So soon, I guess we'll take our break. What I'm going to explain next is how do you know which cells you need to write RK, this disjoint union of classifying spaces of general linear spaces, general linear groups. How do you know which cells you need to create a weakly equivalent cellular EK or CW EK algebra? What cells do you need to give a presentation in this homotopy theoretical sense? So we'll turn out that's controlled by a certain homology theory, and what we'll do is compute that in terms of certain buildings reminiscent of the Tietz building. And then that will eventually lead to our theorem. Okay, but maybe this is a good time to take a break.
Cool. Yeah, we'll, any questions for the speaker for now? If not, yeah, let's break out into our breakout rooms. Let me pause the recording.
Yeah, okay.
Part 2.
Okay, so let me just recap what we're doing in this talk. My goal was to explain an alternative proof of this theorem of Nesterenko and Suslin. So that theorem was that if you have an infinite field, then there's homological stability with slope 1, and the obstruction for improving this result is given by Milnor K-theory. So I was also, if time permits, gonna try and explain what you can say about the next line. And the strategy was going to be to take the disjoint union of the BGLNs of the field, F, and try and write this as a cellular E-infinity algebra. So give some kind of presentation for it, and then use that, CW E-infinity algebra, and use the skeletal filtration to say something about these relative homology groups. Okay. So I got to the point where we were asking the question, how do you know which cells you need to build a CW EK algebra equivalent to R, K, which was the K linearization of the disjoint union of the BGLNs of the field. So it turns out that this is controlled by a homology theory, just like maybe for simply connected spaces, trying to understand how to build CW approximation for that is controlled by ordinary homology, which we denote QEK. It's the EK in decomposables, and has two properties, which are really all you need to know, which is that it is left adjoint. So it commutes with push-outs and colimits, sequential colimits. And it satisfies the property that if you take the indecomposables of a free EK algebra, you just get back the generators, which is honestly what indecomposables should probably be doing. So this leads you to a definition or a construction. It's a derived functor of taking an EK algebra A and collapsing all elements that result by applying 2 array operations or higher. So it's defined by this cofiber sequence. Okay, I'm cheating a little bit here. I'm using here that the 1 array operations in this opred are contractible, at least when n is at least 2. Okay, now the point of these properties that I've given is that if you start out with something cellular as an EK algebra, you get something that's cellular as one of these functors out of natural numbers into simplicial K modules. Okay, so in particular, you can use the homology of these simplicial K modules to get a lower bound on the number of cells you would need to describe your A as a cellular EK algebra. Okay, so let me give that homology a name, EK homology. So it's just going to be defined as the homology, the EK homology of A is going to be defined to be the homology in degree D of the end object of these indecomposables. Okay, so I don't want to spend too much time on somehow the general machinery, which I think is familiar to many people. And if it's not familiar, then saying general things about it is probably good enough. The point is that under mild conditions, the type of connectivity conditions that Akil asked about, but also a certain reducedness condition. So we are going to demand that A of 0 is 0. That's why I deleted BGL 0 of F from my infinity algebra. Under these conditions, there's a Horowitz theorem. What it then tells you is that if you have a map between 2 of these EK algebras, that is an isomorphism on homology groups, ordinary homology groups, in a range that looks like this. Okay, so I'm trying to draw a graph of n versus d. If it's an isomorphism in such a range on ordinary homology, then it's also an isomorphism in that range on EK homology. And the first possible non-trivial relative EK homology group is this one, given by the ordinary relative homology. Once you have a theorem of that type, you can set up a general machinery of cellular OCW approximation. Okay. Now, I lied a little bit. There's one more fact you need to know about EK homology, which is how you actually compute it. And the way you do that is using bar constructions often, which really boils down to the fact that EK is in some sense the k-fold product of E1. So let me just state the result, which is due to, in some form, many people. If I take one of these non-unital EK algebras, add a unit to it, I get something that's augmented. It doesn't just have a unit, it has a map back to the unit that I added. If that's true, I can compute the indecomposables, right? There's some there's some suspensions and extra fluff around that you don't need to worry about. I can compute that in terms of a bar construction of this augmented algebra with respect to indecomposables. So what is this construction given by? Well, let's say K is 2. What you should imagine is the geometric realization of a bisimplicial space of grids where the outer squares are decorated by what you augment to. And the inner ones are decorated by your algebra. And when you delete, the face maps are given by deleting one of these walls, vertical or horizontal walls that divide these squares. When you do that, you either multiply using the EK algebra structure or you apply the augmentation. So maybe if you want to try and understand why this is true, you should think about the case when A is free. Then you can model everything involved by space of particles in a k-dimensional cube that can't collide with each other, labeled by your generators X. And then this bar construction is going to be some space of particles where if a particle hits the boundary, everything goes to 0. And then this is some kind of scanning result. It tells you can always zoom in until you see either nothing or you see a single particle, together with the location of that particle.
So, can I ask a question?
Yeah.
Can you think of this as factorization homology on the disk?
Yes, you can. That's why this name is here. So yes, you can. It's relative to the boundary and you use the augmentation at the boundary. Okay, so what is the advantage of having this type of description? Well, the first one is that you can iterate these types of bar constructions. So if you have something that's both here's something that's an EK plus L algebra, the EK bar construction is still an EL algebra. And you can take the bar construction again. You'll get the same answer if you go in a single step. And then by taking L as 1, you get a bar spectral sequence by filtering the one-dimensional bar construction by the number of grid lines here. So what this bar spectral sequence does is that it allows you to compute basically the EK homology from the EK minus 1 homology, or at the very least transfer vanishing lines. The second advantage of this type of description is that it gives you a computation of the EK and decomposables in terms of certain buildings. Okay. So the idea here is that since this bar construction is some kind of co-limit, instead of computing the bar construction for my R, and which is obtained by pushing down this star lower line greater than or equal to 0 EK algebra, I might as well compute it upstairs and then push the bar construction down. And this type of tensor product is going to be described in terms of quotient groups that look like GLN of F mod GLN1 of F. Oh, sorry. No, it is actually fine, sorry. Where the sum of the ni is equal to n. And you might recognize this as the set of splittings, if you sum at least over all these partitions of n, the sum of splittings of f to the n into subspaces, right? This group acts transitively on the set of splittings with a given partition, and this is a stabilizer. So that's what we'll use to understand these EK homology groups. So let me describe what the answer is going to be.
Sorry, Sander, what do you mean by something is described in terms of? This is the value.
What I mean is that it's not literally going to be true that this tensor product is equal to this, but it's going to be a disjoint union of this, and there's maybe going to be some disjoint base point added somewhere.
Thank you.
Okay, without and these are the terms that will appear in the bar construction. The one
without the R lower star, you're saying, right? This is before you do.
And then you push down this guy, and you get a homotopy quotient of this building by a general linear group.
Thank you.
Okay, so let me just introduce notation that sub M is the poset of summand of the A module M, and then a splitting of M indexed by a pointed set is just a function F from X to here, such that the induced map is an isomorphism. So what will come out of this description of the k-fold bar construction is a k-fold split building, which is a k-fold simplicial set obtained by composing the following functor. So it takes X, so it goes from pointed finite sets to pointed sets, and it takes X to splittings F of M divided out by those splittings which have the value at the base point not equal to 0. You take this functor and you pre-compose it with a functor from delta op to the k to finite pointed sets. Sending some number to a finite pointed set obtained by adding a disjoint base point to just the product of these usual ones. Okay, so by just acting on these splittings, which of course preserves the property that f of the base point is not 0, you get an action by GLM. This building already has a name when k is equal to 1 and A is Dedekind. Then it's in fact true that the one-dimensional split building is a double suspension of Charney's split complex, if you've seen that. Now, this is not helpful unless you've seen Charney's split complex, but I'm telling you this anyway because I want to maybe say a bit about why these double suspensions will keep appearing everywhere. Usually when you study buildings, you exclude certain trivial modules or splittings, namely ones where you just split into the module and the rest being zeros. These types of constructions add those in, and it's those types of trivial splittings or flags that end up being responsible for these types of extra suspensions. Okay, so the theorem that relates these objects to EK homology is the following. You can compute the EK homology of R. Remember, R was a disjoint union of BGL n's of F's. You can compute that as the homology of the homotopy quotient of the split building by GLN of F. Now, maybe if you know a lot about this building of Charney, you can use it to do computations, but if not, then the following might be an approach. Try and get rid of the splittings and replace splittings by some kind of flags. Right, that seems easy to deal with and maybe more familiar from the point of view of like the S-dot construction. So what will replace a splitting is something called a lattice. So it's a functor from this product poset to sub M such that each of the maps from the colimit over this subcomplex phi to phi of B is an isomorphism. Okay, so what does this really mean? Let me draw an example in the case K is 2. Okay, well, what this lattice is some collection of sub modules of M, subends of M, that are arranged in a two-dimensional grid. Okay, so we have many of them arranged in a grid. And what these lattice conditions are effectively saying is that this arrangement of summands could have arisen or can arise from a splitting of this corner into submodules. Okay, now some of these lattices aren't very interesting. And so we're going to restrict our attention to the ones that are full. Full means that at the sides, some of the sides, there's 0. So these sides here should consist of zeros. And at this corner, it's the entire module. Okay, so as already said, every splitting gives a lattice. In fact, these lattice conditions are to guarantee that you arise from a splitting. So for K is 2, a splitting you should think of as some grid of submodules such that the direct sum, or that this direct sum of these guys is equal to all of M. And you can map this to a two-dimensional grid of inclusions by summing across like horizontal or vertical lines. So you get a grid where here you have the sum over I prime comma j prime less than or equal to j I comma j of mi prime j prime. Okay. So the non-split building is the one where you take the quotient of all lattices by the non-full lattices. So we collapse these to a point.
There's a question from John.
Yeah.
So do you want to allow the morphisms from the colimit to phi be the inclusion of a submodule, i.e. not necessarily an isomorphism?
Right, sorry, he's right, yes. That was a mistake. This should be the inclusion of a summand.
Okay, thank you.
Otherwise, of course, none of these full guys is ever going to be a lattice. Because I could take a square where all the corners are 0 except 1, which is all of them. Okay, so an example for K is 1 is that this is basically the Tietz building. So what's the Tietz building? That's like the nerve of the poset of non-trivial proper subspaces of f to the n. Okay, and as before, in this case, we're allowing certain degenerate, certain trivial lattices. So what we're going to get is that the one-dimensional, or the non-split one-fold building is the double suspension of the Tietz building. Okay, so here's some remarks on this. Still by naturality, GLM acts on the K-fold non-split building. And you have maps from the suspension, the reduced suspension of dk to dk plus 1. And that leads to the stable building. So a lot of these definitions are due to John Rockness. Okay. So as already hinted at, when you forget splittings, you get a map from the k-fold split building to the k-fold non-split building, which is equivariant for the action of GLM, and so induces a map on homotopy quotients. And the reason I'm sticking to infinite fields instead of finite fields is that if F is an infinite field, then this is a homology isomorphism. Okay. So let me just like quickly outline how you would prove something like this. So it's surjective, and this is this fact that I mentioned that is conditions are to guarantee a lattice comes from a splitting. And here I mean surjectivity of the original map of buildings. To get it to an homology equivalence, what I then need is that the map on stabilizers of simplices is an homology isomorphism. And the basic case from which you can deduce all the other cases is that I need the map from this matrix group. So these are block matrices where one block has size n by n and one has block size m by m. To block upper diagonal matrices, I need this to be an homology isomorphism. Right? This is how the stabilizer of a splitting and a flag that just have one step, how those differ from each other. And so Suslin and Nesterenko proved that this is true if your ring A has many units. Okay, the condition that you have many units is not the same as having infinitely many units. It means you can find enough units, A1, A2, A3, etc., such that every sum of a finite subset of them is a unit. So this is true for infinite fields, right? You just pick some unit, you pick another one, which is just different from that. Then there's three sums that you could make. You pick a third one that's just joined from those, and you keep going that way. So this is true for infinite fields. And so by the Suslin-Nesterenko theorem, you then get this homology isomorphism. So what the conclusion is that the homology of this object, remember this computes the EK homology up to a shift, is the same as the homology of that object. But these we recognized as Tietz buildings, for example. So here's a consequence. It follows from this. The Solomon-Tietz theorem says that T of Fn is n minus 3 connected. So this implies that the E1 homology of R C is 0 for D smaller than n minus 1. The n minus 1 has to do with the fact that there were some shifts, some suspensions going around. There's also a name for the first non-trivial reduced homology group of the Tietz building. That's called the Steinberg module. There's an action of GLN of F, which has a certain presentation, which for the sake of time I won't give. But this presentation allows you to compute the co-invariants. These co-invariants vanish for n at least 2. And so what you conclude from this is that it's also true that the E1 homology vanishes for D is n minus 1. Right, in this homotopy quotient, the connectivity of the Tietz building gives you the first bit of vanishing, and then by a spectral sequence argument, the first possible non-trivial group that's going to appear for the this homotopy quotient are the co-invariants of this group acting on the first non-trivial relative reduced homology groups. So what we proved and what powers our results is that you can do better when k is 2. So whenever you have a, let's say, two-dimensional grid of inclusions of submodules, what you can do is restrict just to these two outer edges. So a two-dimensional lattice maps to two one-dimensional lattices. And the surprising result, which requires you to work over a field, and is only true when n is equal to, or when k is equal to 2, is that that's an isomorphism. Okay, so this boils down to the fact that the only way that this square of subspaces of a fixed vector space, the only way that this can be a lattice is if V0 is equal to the intersection. So these two one-dimensional lattices determine the two-dimensional lattice uniquely. So how does that help? Well, this guy is highly connected. It's n minus 1 connected. This is also highly connected, and if you smash them together, you get something even more highly connected. So what we're going to get from this is that the E2 homology vanishes if D is smaller than 2n minus 2, and otherwise it's given by the co-invariance of the first non-trivial reduced homology group, which is the Steinberg module tensor itself. So the question is, what are these co-invariants? This is really hard, it turns out. So what you observe is that this Steinberg module, the Tietz building is not just n minus 3 connected, it's also n minus 2 dimensional, which means that the Steinberg module is the kernel of a differential. So it lives inside of the chains, which are just a free abelian group on the full flags. And you can define a pairing on this by declaring that these full flags are an orthonormal basis. So by construction, this pairing is GL n of f invariant, and we can restrict it to the Steinberg module, which gives you a map out of the co-invariance to Z. And what we proved that this is an isomorphism. So we also computed that these co-invariants are given by Z. So this was actually quite hard linear algebra to prove. And all these E2 homology groups right, so this is just a number of copies of Z in varying degrees. They have a ring structure which is that of a divided power algebra. So when you take the bar spectral sequence to go from E2 homology to E3 to E4 all the way to infinity, what's going to follow from this is that for d smaller than 2n minus 2, you get the same vanishing line as for E2 homology. But on the line, d is equal to 2n minus 2. What you're going to get is the indecomposables in this divided power algebra, which you can work out, but they're all torsion. So in particular, if I'm going to work over the rationals, they're going to be 0, which I'll do soon. So the reason this is related to a conjecture of Rockness. So let me just quickly describe what he did. So he gave a filtration of this K-theory spectrum. With filtration quotients given by these stable buildings, the spectra that I built by assembling the K-fold non-split buildings for all K, homotopy quotiented by GLN of F. And so what our result proves is that this is 2n minus 3 connected. And the first non-trivial homotopy group is torsion. So this is the conjecture that we proved. It's actually part of a set of conjectures, and I recommend you read some of John's notes on his conjectures about the rank filtration. The spectral sequence that you get from this filtration of algebraic K-theory is very interesting, especially rationally. And so one conjecture is that it's in some way related to the motivic spectral sequence. If that's true, then this gives you maybe a way of proving something about the weight filtration on rational algebraic K-theory. But we don't know that this filtration, as far as I know, we don't know that it's related to the weight filtration. Okay, so in the remaining time, I want to actually get to this theorem of Nesterenko and Suslin. So what I'm going to do is work over Q, work over the rationals. This has some advantages. The most important is that infinity algebras over Q are just the same as commutative algebras. So when I take free E-infinity algebras, I might as well take free graded commutative algebras. And that's going to simplify a lot of the computations. Of course, in the paper, we work over the integers. Okay, so what do we get out of our result as a vanishing for the E-infinity homology of RQ? So we're going to get a range of zeros below a line of slope 2. So this entire range here, you get zeros. That's the vanishing result combined with the computation of the double Steinberg covariance. To understand the remaining cells in the presentation, I need to know a bit about these groups that appear in these places. Right, those are like the low degree, low rank cells that go into the presentation. And to do that, to understand what those are, I can just study some of these low rank groups. Now, we all know what GL1 of a field is. It's just the units. So what that's going to mean through the Algebraic theorem is that the infinity homology in rank 1 of RQ is just going to be equal to the rational homology of this group. And this is just some free graded commutative algebra. Much harder is to understand what this entry in rank 2 is doing. And so for that, we use a computation of Suslin, which says that, okay, so this BF star is going to generate an entire E infinity algebra freely. That E infinity algebra in rank n, the group is going to be the group of monomial matrices. They're like permutation matrices, but instead of having a 1 in each entry, there's an element of a unit of your field. That's what BGM2 is. That's a monomial matrices. Relative to these monomial matrices, Suslin proved that the rational homology is 0 for star less than or equal to 2. And it's something called the pre-block group of the field for star is equal to 3 tensor Q. And that turns out to be what's going to appear here. Okay, so I've told you what these remaining entries in this little area here are going to be. So what I'm interested in is studying not the absolute homology of R, which is something I'll be able to maybe get from a presentation. I want to understand the relative homology of the stabilization map. And to do that, what I can do is kill off this generator here. Rationally, working relative to the stabilization map is the same as killing off, using a cell, the generator in rank 1 degree 0. And so what I've told you now is that this has cells that look like F star, lambda 2 F star, etc. here. That then here there is a pre-block group, and there's a vanishing line of slope 2. And from this picture, you get a CW approximation that only has E infinity cells in the range indicated by this picture. The associated graded of this CW structure is going to be a free graded commutative algebra on some generators, x, ni, di, where these bi-degrees, ni and di, are compatible with this picture. And you're going to get a spectral sequence from the homology of the associated graded, or it should have been R, or no, A, to the homology of A. So let's just think about what that means. There's no generators at all below this line of D is equal to N. So when you take the spectral sequence, which is the free graded commutative algebra on certain generators, it's just going to have no entries in that range. That's going to give you the slope 1 vanishing range. On this line, the only generators you have are F star. The only relations that are going to be imposed are going to come from this pre-block group. What it's going to do is impose the Steinberg relation. So you read off just from this picture that what's going to appear on this line D is equal to N is quadratic, generated by the units, with relations imposed, with imposed relations being the Steinberg relations coming from the pre-block group. So that proves this Suslin-Nesterenko theorem. But of course, from the picture, you also get information about the next line. Because with a bit more knowledge, you see that there's not so much on the line just above D is equal to N. on the line D is equal to n plus 1, you basically have the second exterior power of the rationalized units, what remains of this pre-block group, and then zeros. So it's going to be presented in, it's going to have generators in just a few degrees and then relations imposed later. At least that's what you might expect. And so that's what something we also deduce from this picture, a description of the next line. And so let me give the precise statement. The precise statement is that there's a map from the third Harrison homology of Milnor K-theory. So this is a summand of Hochschild. To the, well, Milnor K-theory generators of this line. And this map is going to be an isomorphism for n at least 4. So if you know that Milnor K-theory is causal, then you know that the only place in which the Hochschild homology is, the only degree in which the third Hochschild homology can be non-zero is degree 3. Implicitly, the Harrison homology can only be non-zero in degree 3, which tells you that the map to this indecomposables of this next line with respect to Milnor K-theory is concentrated in degree less than, in degree less than or equal to, in degree less than or equal to 3. So what that buys you is that if you know that the Milnor K-theory is causal, then you know that the next line of the unstable homology is generated over Milnor K-theory in finitely many degrees, and in fact in degrees n less than or equal to 3. Okay, so what I should now say, I already mentioned it before, that this is the last thing I'll say, that this is the case. This follows from conjectures of Beilenson and Barshin if the characteristic of F is finite. If you want to read about this, there's a paper of Positzelski, which is called Mixed Arden Tate Motives, where he talks about this with finite coefficients. So probably it is true that this next line is generated over Milnor K-theory in finitely many degrees, but we only know it in particular examples. For example, an easy way that the Milnor K-theory can be causal is if Milnor K2 happens to vanish, which we know for some fields. Okay, so that's what I wanted to explain.
All right, let's thank the speaker. Any questions for Sander?
I have a question about the divided power algebra structures.
Yeah.
So there's these operations that Bausfeld and then Dwyer constructed, and I guess Fress has given an explanation for them in his thesis, and Michael Ching has some notes as well. I'm curious if these divided power structures are coming from some underlying structure on the E-infinity algebra that you began with. Like, is there some extra structure on BGL that allows you to notice this? Or you just compute the group and this is what's there?
Yeah, so you know a priori it's going to be a ring because the E2 indecomposables, well, the second bar construction is still an infinity algebra. So you know there's going to be a ring structure. And then our computations are explicit enough. Right? It's a Z. We know exactly what map gives you the Z. We can like find elements in the Steinberg modules that map to the generator. It's explicit enough to just completely do the computation. So I think that fact is a computational fact. It would be good to have a better description of this. Like some information, qualitative information about these lines that you get without just doing a complete computation. because I should maybe mention is that this computation of the double Steinberg covariance, before I said we do basically everything over semi-local rings with infinite residue fields. That's the one thing we were not able to prove for these semi-local rings with infinite residue fields, computing the covariance of the Steinberg model, tensor the Steinberg module. So maybe if one wants to make progress, one shouldn't try and compute things more explicitly, but add qualitative information about the homology of GLM with coefficients in the Steinberg tensor the Steinberg, which could include understanding what operations a priori have to exist in it.
Any other questions?
I have a Milnor K-theory question.
Yeah.
So Milnor K-theory also arises as the top the nth motivic homology or hn of weight n motivic homology, but also due to Taro.
Mm-hmm.
And so I was wondering what is there a relation between motivic homology, or this top weight motivic homology, and this relative homology of GLN?
So I'm not aware of any relation, even conjectured, of that form. However, and again, I think it's worth reading John Rockins' notes on this. In this rank filtration spectral sequence, Milnor K-theory also appears. It will appear on the first column, and it's built by, or it appears by a D1 differential mapping in this column here. So that's maybe a reason to expect that this rank filtration spectral sequence is related to the motivic spectral sequence, because Milnor K-theory appears there also in like some kind of edge location. So that's maybe a more reasonable thing to conjecture to be related to the motivic spectral sequence.
Thanks.
I guess you could, sorry, you could ask whether, excuse me. So let's say indecomposable K3 of fields is related to the block group, and that looks like that, somehow fits in with the appearance of the pre-block group. So I guess one might wonder to what extent one can go like one step further and, say something similar about K4 of fields, I guess Goncharov has some work in that direction.
Yeah, so, I mean, I can say a bit more. So one thing that John also proves is that if you look at what is going to come from this term given by the pre-block group in the rank filtration spectral sequence, on E2, that leads to the actual block group. So it also shows up in this story. If you want to push this, at least R-like homological, group homological approach further to get information about higher K groups, at first sight, it seems like you would have to know something about like the homology of GL3 of a field, which is a very difficult question. However, it might be possible using this type of approach to get some description of the entries on, say, the rank spectral sequence, or the infinity homology, get some description of it in terms of certain complexes of symbols, like Goncharov has constructed many of. That might be something you could try to do. Maybe you can map some of these complexes into infinity E2 homology, something like that.
Yeah, thanks.
And I see that John posted his notes. Yeah, they were quite inspirational for some of the stuff we did.
May I ask you, it appears that you are mostly interested in rational coefficients, and Wasilewski mostly treated torsion coefficients. What is the main difference between these two settings?
So I wouldn't say we're mostly interested in rational coefficients. I mainly picked it at the end for the sake of exposition. However, it is my understanding that rationally, the algebraic K-theory of fields is much less understood than with finite coefficients. So that is maybe a reason to be more interested in that particular case. Was your question what the main difference was between the rationalized algebraic K-theory of fields and the finite coefficients?
So as far as I know, the Voevodsky, Psitselsky depended on certain conjectures. And what about you? Or do you need any conjectures to work?
So none of what I've talked about here depends on any conjectures, or if it is, it's formulated conditional on those conjectures. There are, I think, more. There's more things that are unknown about the rational algebraic K-theory of fields. I don't know whether. I mean, I guess the big open conjecture there is the Solen-Valenson conjecture. But we don't say anything about it or use it anywhere. So.
Okay, thank you.
Other than the regulator map, I don't think we understand the K-theory of the complex numbers mod torsion.
Yeah, as far as I know. I mean, I guess you know that it's uncountably generated vector space or something in some degrees, but yeah, not much is known.
Okay, if not, let's give our speaker a round of applause. The 31st October.
Okay, thank you.
Okay, thank you.